This is going to be part one of my series of discussions on naming organic compounds. Of course, when we discuss things like this, we're going to follow systematic nomenclature because that is the type of naming that we have rules to follow. Usually, for other organic compounds, we only memorize their common or trivial names, but well, what's to discuss if there's only memorization, right? So we will only focus on systematic or the IUPAC, specifically substitutive nomenclature. There are other non-substitutive methods, but we will only discuss that in the advanced videos. Now, basically, for most organic compounds, even the simplest ones, their parts in the name would always include the parent chain and then optionally substituents. We first focus on the parent chain. Usually, the parent chain is essentially the most important part of the compound, which is commonly the longest consecutive chain of carbons, or the longest set of carbons that form a straight line. And therefore, when we talk about parent, it's inevitable that we talk about length or number of carbons, so we use prefixes to denote that. And this should be very familiar. Meth, eth, prop, but. For example, if I have alkanes, we have here methane. If I have 2 carbons, I have ethane. If I have 3 carbons, propane, so on and so forth. And I want you to notice that the first 4 prefixes are quite unique to organic chemistry: meth, eth, prop, and but. However, when you start from 5 carbons onward, you go back to the mathematical prefixes. Like we get this from penta, we get this from hexa, then you can assume hepta, octa, nona for the next number of carbons. I do suggest, however, that instead of using the prefix penta, just use pent. Remove letter A because letter A means something. It means a single bond or alkane. And not all the time we have purely single bonds, right? So it's safer to just call it pent, hex, hept, so on and so forth. That's just for the parent. Don't forget that we have what we call substituents, which are basically functional groups or alkyl groups. When I say functional groups, double and triple carbon bonds are included there, okay? So the general format for the IUPAC name is prefix parent suffix, wherein the parent, the length, which is meth, eth, prop, is in the middle, and then we assign prefixes for the low priority substituents, which is the focus of this recording. The suffix is reserved for what we call as the highest priority or the principal functional group. So apparently there is some priority or hierarchy going on in the functional groups, but we will reserve the suffixable functional groups for part 2. So we focus more on the prefix for this recording. There are a lot of rules already to consider at that point still. And I put a blank area here because I want to discuss something. Notice that our suffix for the alkanes is ane, A-N-E. I want to note that the real suffix here is letter E. Because there are times that when you add a functional group to an alkane, the AN remains. For example, if I have ethane. If I remove one of the H's and then I replace that with OH for alcohols, the name only becomes ethanol. And notice that AN stays. If AN was really part of the suffix, the name would have been ethol, but the AN stays. That's why I want to include the bond type, whether AN for single, EN for double, or YN for triple here, because this is technically not something that we remove all of the time. Now, again, part 1 would be dedicated to the low priority groups, and the parent compounds here, or the parent chains, would be very obvious. We will talk about more obscure, more complicated, more confusing examples in parts 2 and 3. So let's get to it. Examples. First, we have these simple alkanes with only one substituents, just to get the ball rolling. For one, we don't have any substituent, so you just name it as it is. 3 carbons, all are single bonds, then we end with letter E. Because as you know, in this video, we will not put any other suffix except letter E, just to avoid getting too much ahead of ourselves. For 2, we still have the same parent, which is propane. But notice that now I have this substituent. 1 carbon, so that's meth. But once it becomes a substituent, we replace the suffix ane to il, YL. And In order to make sure that we can accurately locate where the methyl is, we need to indicate that the methyl is located at carbon number 2 of propane. How did we count that? Propane has 3 carbons, this is 1, this is 2, this is 3. Even if you count backwards, 1, 2, 3, your methyl will always be at number 2. So this is the complete name. We call these numbers as locants because they tell you the location of a substituent. For 3, it's almost the same, but this time you have a chlorine instead of a methyl. In this case, the prefix would be chloro. So we have here the name 2-chloropropane. So it's just like you end with O for halogens like chloro, bromo, iodo, fluoro, so on and so forth. How about this? We know this is 2-something propane, but we just need to know what this something is. The name of this is a methoxy group. Simply because it's just a combination of a methyl, right, 1 carbon, and then an oxygen, methoxy. And note that we read from the outside to inside because that's the general rule. So if I have 2-methoxypropane, you see it has a flow in the name or in the structure also. Methoxypropane. You're going from top to bottom, something like that. For 5, this is the only time that I will introduce to you a suffix. So like if I have 3 carbons, there is no double or triple bond. And then the letter E, once again, will be removed because we know that the OH has the suffix all. And usually, we even have to note that that is at number 2. But once again, because suffixes have their own set of complicated rules, we will not focus on principal groups like for alcohols. So back to halogens, we have bromine here. And take note that we still have propane as our parent chain. Some people will have this mistake that they count this as a carbon. But remember this, if this point is directly beside an atom like bromine, this is not anymore carbon. This now directs to the atom bromine. So this becomes 1, this is 2, this is 3. So you have bromine at number 1. So we write that appropriately as 1-bromo propane. In 7, you have here 2 possible alkyl chains. This one has 2, this has 3. And as I have mentioned a while ago, the parent is the longer one in the case that you have conflict. So this becomes the parent. We still go to propane. Now, some may say, okay, I have the substituent. How do you name the substituent? I have 2 carbons and then oxygen, so that's F-oxy, ethoxy. So now, if I have ethoxy, where's the number? If you start here at the left, 1, 2, 3, it would be 3-ethoxy. But what if I go backwards, 1, 2, 3? Where would ethoxy be? That would be at number 1. In the case that you have a conflict between 2 possible numbers, in this case 1 versus 3, we choose the lower number. Of course, that would be number 1. So that means that you can actually count backwards, or you can even count from top to bottom, as long as you get the smallest number for the single substituent. And take note that these first 7 examples are easy because they are only monosubstituted. We only have 1 substituent max. What are the substituents that we have? Alkyl groups like methyl, alkoxy like methoxy and ethoxy, and of course halogens. These 3 are what we call as low priority substituents. And when we say low priority, they are always prefixed. They are never found at the suffix. And for the locant assignment, we prefer the lowest possible number. Okay? We go to some more difficult examples, I guess, because in this case, we will have 2 or more substituents instead of just 1. For 8, we have the parent chain here, 4 carbons. All are single bonded. Then we end with E. And now you notice that we have, instead of just 1, 2 methyls. So I need to indicate that I have 2 methyls. And to indicate that, I use multiplicity prefixes. For 2, I use the prefix di, which should be common sense to majority. And I need to note that di has to be indicated by 2 numbers. In this case, since my methyls are both located at the number 2 of butane, I write 2,2-dimethyl. Now, you may ask, and some people, a lot of people actually make this mistake. They just write the name 2-dimethylbutane. But remember this, your multiplicity prefix should be reflected by the numbers before it. So if di means 2, then you should have two numbers here, even if it's the same. For 9, all we did was just to move one of the methyl. There are two methyls here, but we just move one to the other side. So we have one methyl at 2, we have one methyl at 3. So all you will do is to replace 2, 2 with 2, 3, but that doesn't change the fact that we still have two methyls here, right? And we have the parent chain butane. And in 10, this is interesting. If I start at the left, let's say this is number 1, this methyl here would be at 2, this would be at 3, and this would be at 5, right? 1, 2, 3, 4, 5. Now, if I start from the left, if I start at the right, this methyl will be at 2, this is 3, this would be at 4, and this would be at 5. So now we have a dilemma. What do we follow? We have the set of numbers 2, 4, 5 if I start at the right, and I have the set of numbers 2, 3, 5 if I start at the left. So apparently, usually we follow the fact that we find the lowest number. In this case, 2 and 2 is a tie. In that case, you move to the right part, and in this case, you would notice that there's a difference. This is the first thing that's different between the two sets of numbers, 4 versus 3. And 3 is the smaller one, so we choose the combination 2, 3, 5. It would be 2, 3, 5, tri, because there are 3 of them, trimethyl, and how many carbons? 1, 2, 3, 4, 5, 6. 6 carbons alkane. So this is the name. The rule that we just followed is called the first point of difference rule. And it tells you that if I have two possible sets of numbers, you find the first difference upon listing the sets of numbers and you choose the one with the smaller number. For 11, we have your cyclic compound. We know that this has 4 carbons. All of them are single bonded. But to indicate that this is a ring, you have to put the prefix cyclo. And note that this is only cyclobutane. We have a methyl here, so you should write methyl cyclobutane. Now if you ask, okay, where is this located? What carbon is this carbon containing the methyl? It's 1. But notice I didn't write 1. That's because, as a general rule of thumb, if I have a name where writing 1 doesn't actually give you additional clues to the structure of the compound, you can omit 1. And for many cases in cyclic compounds, we omit the substituent at 1. But for 12, it becomes a little different. Our parent is a cyclic compound containing 5 carbons and all single bonded, and it contains 2 methyls here, so that means dimethyl. But look, I now say that we are obliged to write 1,1-dimethyl. All of a sudden, why did we write 1,1 when I just said in 11 that if we have only one carbon holding a substituent, you don't write 1? That is because there are possible compounds. If I remove 1,1, dimethylcyclopentane, well, this is also dimethylcyclopentane, right? This is also dimethylcyclopentane. And that tells you that the moment that you have a name that can pertain to 2 or more different compounds, you are obliged to write the numbers. If in 11, you can do it on your own, regardless of the writing of 1 or not writing the 1 in methylcyclobutane, you will always get the same exact structure. For 13, we have here once again a cyclic compound containing 6 carbons and all single bonded. So in this case, we have 4 methyl groups, right? 1, 2, 3, 4. So that would be tetramethyl. And now the dilemma is just the numbers. And once again, we follow the first point of difference. Usually, in this case, we prefer to automatically place number 1 to the carbon holding the two substituents because that will automatically give you 1, 1, right? So this would be 1. And then, if I go clockwise, this would be 3. Meaning, after 1, my next number is 3. But if I go counterclockwise, 1, my next number would be 2. And of course, 2 is smaller than 3, so we go in this direction. So 1, 2, 3, 4. So this is 5. So my numbers are 1, 1, 2, 5 tetramethyl. So 1, 1, 2, 5. The same with here. So in 14, I have, this could be 2, 2, 4 trichloro or 2,4,4. Of course, between 2,2,4 and 2,4,4, the difference is this one. 2 is smaller than 4, so we prefer 2,2,4 trichloro. And then how many carbons do I have in the parent? 5. Pent, all single bonded. But here, if I start at the left, my chlorine would be 2, 2. My chlorines would be 2, 2, and 5. If I start at the right, it would be 1, 2, 1, 2, 3, 4, 4. So it's obvious. 2, 2, 5 versus 1, 4, 4. And you might say, okay. And many people do this. They add 2 plus 2 plus 5. That's 9. 1 plus 4 plus 4. Guess what? It's also 9. So what do you assume? 4 is smaller than 5? 4 is greater than 2? When you follow the first point of difference, you always start at the left, okay? So you ignore this and this first. You first compare 2 versus 1. In that case, you already have a winner. Of course, 1 is smaller. So apparently, you use 1, 4, 4 trichloro pentane. And this is where a lot of beginners get things incorrect. Many people teach the lowest sum rule, whatever that is, because it's easy to teach. But the apparent thing is there's no lowest sum rule in the rule book, in the blue book of the IUPAC. Notes: the first point of difference rule only applies when there is no principal group. Notice there's no OH, aldehyde, carboxylic acid, ketone, all of those are principal. So that's the only time we can apply the first point of difference. When there's a principal group, things are much more, uh, you know, jumbled up. It's a little more difficult. And sometimes the first point of difference fails. Our dependence on FPD is the fact that we have choices that have different sets of numbers, like 245, 235, 255, 144. But for example, there are cases you have two options and they have the exact same combination of locants. It's like 24 versus 24. We have a lot of that in our next examples. So how do you resolve this? What's the tiebreaker? The tiebreaker is alphabetization. So you alphabetize. For example, in 16, if I start at the left, my methyl would be 2, so that's 2-methyl, and my chlorine would be 4-chloro. If I start at the right, this would be 2-chloro, and this would be 4-methyl. And this is what I was talking about. It's 2,4 versus 2,4. The first point of difference fails because the numbers are the same. So in this case, alphabetize. We give chlorine the smaller number because it comes in the alphabet first, then letter M. So we use 2-chloro, 4-methyl. So it would be 2-chloro, 4-methyl, then 5-carbon parent pentane. The same with 17. I can assign this methyl as 1-methyl and then this ethyl as 3-ethyl. Or alternatively, you can switch that up, 1-ethyl, 3-methyl. But since letter E precedes letter M in the alphabet, we give this the smaller number and then methyl the larger number. So this now becomes 1-ethyl, 1-ethyl, 3-methyl, and then cyclic. And then my cyclic compound has 5 carbons, all are single bonded. Okay. Now, if I have 18, I have here a cyclic compound containing 6 carbons and all are single bonded. It's iodine versus methoxy. It's either 1, 2 or 1, 2. So what do we follow? Well, this is letter I, methoxy is M. In the alphabet, I precedes M. So apparently, we will have 1 iodo, 2 methoxy. So let me write that. 1 iodo, 2 methoxy, cyclohexane. Now notice, in 18, I'm already comparing an alkoxy to a halo group. And remember that alkyl, alkoxy, and halo are all low priority. So that's the only time we can follow alphabetization if all are of the same rank. Remember, these are all low rank. They are the lowest possible functional groups in our hierarchy. 19, fluoro is F. Then what's this? 2 carbons and oxygen. That's ethoxy, right? So what goes first in the alphabet? E or F? Of course, it's letter E. So this will be assigned the smaller number 1 and fluorine the larger number 2. So we have the name 1 ethoxy, 2 fluoro, then the same parent, cyclohexane. Notice that I'm alphabetizing as a tiebreaker in the assigning of the locants, and also when I write the name, I make sure I alphabetize them. Right? Now look at this, 20. This is quite interesting. We know that we start here as number 1, so we have here 2-methyl, and we have here as 3 2-carbons, ethoxy. Here, we don't have a tiebreaker of alphabetization because the first point of difference applies. If I start here at the left, I will have 3 4. If I start at the right, I have 2 3. So 2 3 wins. Okay? So this would be, how do I write that? I write that as 3 ethoxy 2 methyl pentane. And notice this, even though my ethoxy has the higher number, I still write it first. So that means that the way that we write the prefixes is independent of the number and solely dependent on alphabetization. So your numbers can jumble up like 3 2, 1 4 3, 4 1 1 6, but as long as your prefixes are alphabetized, that's the correct one. So for 21, I have here another dilemma. It's 2 4 versus 2 4. So first point of difference cannot be used. So we alphabetize. So this is ethoxy. This is methyl. So of course, this is first in the alphabet. So we give this the smaller number. So that's 2 ethoxy, 4 methyl. So 2 ethoxy, 4 methyl pentane. Okay, for 22, in this case, look at this. We have a lot of things going on. We have here, let me write first the parent. We have cyclohexane, right? Cyclohexane. Then you have here a bromo, methoxy, and methyl. And here, we can try using the first point of difference, meaning get the lowest set of numbers. So if I do that, I have a lot of possibilities. You can actually pause this video and then try to list all the possible lists of or set of numbers or locants. Anyway, let me answer this already. If we start here, we have the set of numbers 1, 2, 4. If I start here, we have 1, 3, 4. If I start with methyl and go counterclockwise, it's 1, 2, 5. It's like 1, 2, 4, 1, 3, 4. Let me write that. 1, 2, 4, 1, 3, 4 versus 1, 2, 5. This one automatically loses because 3 is larger than 2. So 1, 2, 4 versus 1, 2, 5, obviously we choose this because 4 is smaller than 5. So we have here 1, 2, 4. We follow this arrangement. And apparently, this is just out of pure luck. It's just a coincidence. This is also the way that we alphabetize because, right, we have 1 bromo, letter B, then 2 methoxy, then 4 methyl. Right? Meth O comes first before meth Y. So this is really the proper arrangement. Now, things change here because in this case, you have here 2 methyls. And just with the case of 13, 1, 1, you are forced to give this number 1 because there's no other 1, 1 except by doing this or putting this as 1. So if I go clockwise, this would be 1, 2, 3. This would be 4. This would be 5. If I go counterclockwise, this would be 3. This is 4. So we go this way. But remember that you still alphabetize when writing. So B first, as always. Then methoxy. Then 1,1 dimethyl. So we have absolutely no regard for the arrangement of the numbers. 4, 3, 1, as long as it's alphabetical. Then cyclohexane. Now you may ask, B, then M, then D, shouldn't this go first? And the thing is, we ignore multiplicity prefixes, meaning you still consider the methyl, not the di. So if there's tri, tetra, penta, that's not part of the arrangement by alphabetization, okay? Just a very important rule. So I don't have space to write that, but that is very important, so I think you should take extra caution with that case. This slide shows you examples containing double and or triple bonds, and this is interesting because now we change a little bit our suffix. So we have butane usually, but now we have a double bond, so I replace AN with EN. But remember that a double bond is a functional group, and for every functional group or substituent, you are obliged to write its locant. So this double bond is between 2 and 3. If I start at if I start at the left, if I start at the right, it still is between 2 and 3. So what do I choose? Do you write both? No. You only choose the smaller number, which is 2. So the name is butene. Or some people prefer writing 2-butene, but I prefer the first one because this tells me that number 2 describes En, which is exactly next to it. Sometimes, and this is only my problem when I was a student, if I separate 2 and En, which this number 2 describes, I tend to get confused, especially when the names of the compounds are very long. For 25, if I start at the right, my double bond 1, 2 would be at number 3. If I start, wait, this is at the left, I mean. If I start here at the right, my double bond would be at number 1. So obviously, between the numbers 1 and 3, number 1 is smaller. So we choose this as the number. So it's but1 in, or alternatively, equally correct, you can call this 1-butene. For 26, it's symmetrical. So either starting at the left or the right, you have here the numbers 1, 2, 3, 4. The first double bond at number 1, and then the second double bond will have the number 3. So if I have two double bonds, I'm also obliged to write the multiplicity prefix di. So it's diene. And the numbers for those two double bonds are 1 and 3. And finally, the 4 carbons should be indicated but. But here, it's a little incomplete because these are consonants. Technically speaking, this is not allowed, so you should put a vowel in between, usually A. This is because, and I think this is practical, because if I don't put A, you pronounce this as butadiene. It's kind of difficult to pronounce. But if I add this, we call this butadiene. It's easier to roll off the tongue. For 27, we now here have a conflict. I have an alkyl group, this is a methyl, and I have a double bond. And remember this, double and triple bonds are higher priority, meaning they are preferred over alkyl, alkoxy, and halo groups. That means that in the case of this double bond, okay, we have to give the double bond the smaller number, meaning the first point of difference rule will be ignored. So, if I start here at the right, my double bond will be assigned number 3, right? If I start at the left, my double bond will be assigned number 2. So, we prefer starting at the left. So, we have here the parent chain 1, 2, 3, 4, 5. So, pent, my double bond is at number 2. And in that case, my methyl would be 1, 2, 3, 4. So that's 4-methyl pentuene or 4-methyl 2-pentene. For 28, this is the same. Remember, we prefer this over this. So we have to write this as number 1. At this point, it doesn't matter. If I go here as 1, my bromine would be 4. If I start here as my number 1, my bromine will still be 4. So luckily, whatever you do here, you're supposed to come out with 4-bromo, then cyclo, pentene. And remember, if I have a cyclic compound, we can ignore the number 1 for the substituent at number 1. For 29, we have a double bond, so once again, we have diene. But how do you number this? Let's say that this would be number 1 for you. There are 2 carbons that can become number 2, right? It's either this one, number 2, or this one. And there's something very wrong here. If you go upward, that's incorrect. The rule is, if you start with a carbon containing a double bond, you're obliged to move next to the carbon that holds the other carbon that holds the same double bond. You cannot leave that behind. In that case, this double bond, the next one is between 3 and 4. Of course, the first double bond will be given 1, the smaller double bond will be 3. So we're back to 1,3 diene. And remember, the parent chain has a cyclic portion containing 5 carbons. 2 consonants, T and D, we add letter A in between. For 30, it's a little bit different because you cannot count number 1 here anymore. Why? Because this is just a double bond. On the other hand, you have here a double bond and an alkyl group. So, in this case, you will have here like 1 in and one methyl, which makes it win in the first point of difference. It wins actually in most of the rules that we've followed so far. So we have no choice but to follow this numbering. So we have here 1 methyl. Then the exact same name as 29. Cyclo, penta, it's still 1, 3, right? Diene. Now what if I have a double and a triple bond at the same time? Remember this, double and triple bonds are same in rank. So, remember what I told you a while ago? If they are of the same rank, and look at this, if I start at the left, my double bond would be 1, my triple bond would be 4. If I start at the right, this triple bond has 1, and then double bond has 4. So we cannot use the first point of difference. So what do we follow? Alphabetization. So this is En, the triple bond is Yn. This comes first in the alphabet, so we choose 1, 4, giving this the name pent. The double bond is at 1, the triple bond at 4. Now, we have some examples where we can try to apply all of the principles we have learned so far. First, with 32, it's very easy that the parent is just cyclohexane. And then now we have here one carbon with 2 methyls, and then this carbon at the bottom has 1 ethyl. Do we follow alphabetization? No, because remember, alphabetization is just a tiebreaker. We first follow the first point of difference. Since this one has 2 methyls, then this would be 1. Then this would be 3. So this is going to be 1, 1 dimethyl, and then this is 3 ethyl. But what do I write first? Remember, we follow alphabetization when writing, regardless of the numbers. So we first have 3 ethyl, and then 1, 1 dimethyl. Remember that we don't consider the letter D of di, but the M of methyl. So E before M. So this is the final name. For 33, things are a little bit different, well, except for the parent, which is still cyclohexane. So now we have here 2 methyls at this carbon and 2 substituents at the bottom, methyl versus ethyl. So either way, you will have 1133 or 1133. So now you cannot use the first point of difference. It's a tie. So now you use alphabetization. And it seems like the one with the letter E, with ethyl, will have to have the smaller number. So we switch things up. So we now have 1 at the bottom and 3 at the top. So that would be 1 ethyl. And then remember we have 3 methyls. So that would be 1, 3, 3 trimethyl. Then for 34, just the same almost as 33, we just change 1 methyl to chlorine. So now, this is another battle. 1133 versus 1133. So it's alphabetization battle. MC versus ME. And this time, C is chosen before E. So we go back to this carbon being number 1 and this one being number 3. So now how do I write that? You first write the chloro, then the ethyl, then the methyls. It will be like 1 chloro, 3 ethyl, 1, 3 dimethyl, cyclohexane. So I hope you're getting the hang of the rules, both in assigning the locants and writing the entire thing. For 35, this is no questions asked. We have here our double bond assigned as number 1. So this would be cyclohexene. But now the next question would be, how do I give number 1? Do I start here as 1 and then this is 2, then clockwise, or do I go 1, 2, or counterclockwise? And we can try to check if the locants are different. So if this is 1, 2, 3, this is 4, and this is 6. So if I choose this one, this is 1, 2, this is 3, and we already have a first point of difference, right? So a while ago we had 1, 4 going clockwise. Going counterclockwise, we have 1, 3. So apparently counterclockwise would be the way to go. So we don't choose this. So we have 1 for the double bond, and we don't need to write that anymore, right? Then 3 for this methyl and this ethyl, and then for 5 for these 2 methyls. So we have here an ethyl at 3, and then 3 methyls, 1 at 3, and 2 at number 5. So again, remember, even if the numbers are quite large, 3, 3, 5, 5, it doesn't matter because we have to always be under the principal functional group. And then 36 is the longest one so far, which is nice because we'll have more complicated examples like this later on in part 2 and 3. Here, obviously, I can start in, well, we can start here or here or here, but out of those starting points, this is the only one with a double bond. So this has to be number 1. Then 2, 3, 4, 5, 6, 7, 8. Yeah, that should be the longest chain. So we have oct. Then, we have here two double bonds. The first double bond is at 1, and then the second double bond is between 4 and 5, so at 4. So that would be octa, 1,4 diene. And then we have a methyl at 6, a methoxy at 5, MO for methoxy, and chlorine at 7. So of course, alphabetizing that, oh, I almost forgot. Another methyl at 4. So alphabetizing that, C first, then methoxy, then methyl. So that would be 7 chloro first, then 5 methoxy, then we have 4, 6 dimethyl. Again, ignoring the letter D of di in alphabetizing the prefixes. And I guess I've covered everything. The two double bonds, these two methyls, methoxy, chlorine. Okay, so this is the final name for 36. So I hope that I've explained the first point of difference, alphabetization, principal groups for our hydrocarbons with these examples, and we will go to part 2 and 3 in the next recordings.